All right, good morning and happy Thursday morning. I'm planning on doing a LeetCode contest 321 from a couple of weeks ago. Let's see here. Okay, here we go. Start up some music and start jamming. Okay. It is 5:27 in the AM and it's time to shine. Here we go. All right, open these guys up. Oops. There we go. Okay, find the pivot integer. Sum of 1 through x inclusive equals the sum of all elements between x and n inclusive. 6 is the pivot integer since 0, 5, 6 equals 6, 7, 8. There is no pivot integer for 4. 1 through x, x through n. Okay, so we should be able to compute the sum from left to right and right to left. I suppose, right? Let's see. Recompute sums, right, prefix sums from left to right and from right back to left. Given n, let's do this. N inclusive. So left equals 0 times n plus 1. R equals 0 times n plus 1. Actually, yeah, so we'll add these from left to right and right to left, and when they're equal, that's the pivot element. Return -1 if the pivot element's not found. For I in range. Let's see, L sub 0 equals 1. R sub n equals n. Range 1 to n. Oops. Inclusive. L sub I plus equals L sub I minus 1. And for I in range n minus 1 down to -1, non-inclusive by -1. R sub I plus equals R sub I plus 1. Print on R. Okay. That did not work. Need to be monotonically increasing sums, right? Okay, so hold on. I plus 1 for I in range n. Right, okay. Same for R. Oh. Range n plus 1, oops, yeah. 1, 2, oh wait, hold on. Get rid of the plus 1 and do just from 1 to n plus 1 and 1 to n inclusive. Okay. So 21 should be, what the heck? L sub I minus 1, list index out of range. Oh. plus what? Oh, 1 to n plus 1 is n. So there's only n of these things. So 21 is the pivot element here. Each ith pair. So we can return I plus 1 if they're equal. Mm-hmm. Does that work? Can I destructure it? Yeah, okay. Okay. 6, 1, -1. 4 is not correct. Or wait, hold on. Oh, okay, hold on. No, that was right. Oops. 6, 1, -1. Yeah, that's cool, right? Okay. So that took about 7 minutes. About 7 minutes. Station, which is AC. All right, okay, so that's cool. Few solutions. Prefix sums from left to right and right to left. Right. Pre-compute prefix sums. To find the ith candidate. Yeah. An ith candidate index where the sums are equal. That sounds good. And JavaScript. Three. Rest. C++. Okay. I wonder if it's just easier just to say this instead of zipping them. In if L sub I is equal to R sub I. It looks a little bit cleaner. In this case, we can return I plus 1 for I in range n if L sub I is equal to R sub I, or -1. I'm not sure if this will work or not. This index out of range, I in range n. Six is not a valid return. Oh, yeah. 6 and 1. Okay, so -1 doesn't work. Yeah. Okay, so that doesn't work. 0 doesn't exist. Okay, this is good enough, right? Let's take this and then move on. Actually, I wonder if this would be, maybe I can simplify it a little bit. 0 to n inclusive. No. That doesn't work. Okay, whatever. We'll just keep it 1 to n plus 1 inclusive. Yeah, it doesn't need to be perfect, right? This is good enough. Just take it and go. All right, so from 1 to n inclusive, let's set the ith value. From 1 to n inclusive is n. Here 'Let's make sure these are cool. All right. So if L sub I is equal to R sub I, then we'll return the 1 based index of I. Looks good. Okay, yeah, nothing too fancy. Keep it super simple. one base index of I, or is the same thing. All right, so the prefix sums from left to right. Prefix sums from right to left. Left ith value is equal to right ith value, return the one based index of I. Otherwise, the pivot element is not found. Looks good, it's cool. Okay. Kotlin time. Okay. Oops. We have n. It's one. So if else of I is equal to R sub I, return I plus one, otherwise return -1. Looks good. Okay, and rest is next. Always saving the best for last here. Okay, make this guy mutable. Oops. I wonder if I can collect it actually. Let's do this. Let's do 0 to n, or 1 to n inclusive, dot into iter dot collect as a vector of integers. Okay, just debug this output. Iterative view size. So okay, it's cool. Okay, something like that. Oh, side 32. Oh, oh, dang. N minus 2. Oh, crap. Oh, that's not right. 1 through n inclusive. Let's do this. Oops. These guys out and see what's going on. Looks wrong. 8. What the heck? 1 through and inclusive, and then what is going on? R sub I plus 1. What? Prefix sums is wrong. Oh, n minus 2 inclusive. That looks good. Okay. If n is greater than 2. Yeah, it could be worse, could be better, whatever. Good enough. Okay. Your prefix sums, left to right, right to left. Okay. And we have 1 hour, 6 minutes left. It took a while. 1 hour, 6 minutes. Okay. T becomes a subsequence of S. Append the characters D-I-N-G. C-O is the same thing. There is no D. So I need to find the first missing character, which is D. First missing character from left to right. always move J. Only move I when we can, and then return. Oh, we always move I, but only move J upon match. Then the remaining J will be what we need. Turn. Zero, 1, 2, 1, 2, 3. Length of T minus J plus 1 for it to be inclusive. 5, 1, and 6 is off. Oh. 405 is cool. Looks good. 1 hour, 6 minutes, 1 hour, 3 minutes. So that took about 3 minutes for the implementation in Python 3, which is accepted. Yay. Nothing too fancy. Perform a linear scan of the input strings S and T using index I and J correspondingly. Kotlin, JavaScript, Python 3, Rust, C++, already. .405 is good. Already. Oops. There we go. Okay, JavaScript. Oops. Oops. If S of I is equal to T sub J, then J, always comment I, T dot length is J. Nothing too fancy, right? Okie dokie. Okay, Kotlin. Okie dokie. Looks good. That's cool. Okay, and then Rust is next. Rust, where's Rust? There it is. Okie dokie. Uh-oh. 9:32. All right, that's cool. Nothing too fancy. Okay, and then we have 58 minutes left. 58 minutes. Okie dokie. Monotonically decreasing Q. Some sentinel value. I wonder if we can do this recursively, like a monotonic stack, like monotonically decreasing, monotonically strictly decreasing, right? Monotonically strictly decreasing. Yeah, we can stick it in a queue for now, right? Just create a new linked list. I'm pretty sure that's not how you want to do it though, but whatever. Articles. Whatever. Let's just do this. All head a dot append head dot value. Let's just do this. Node equals head. Node. Node equals node dot next. Let's see. So file length of A and top of stack exceeds or meets the node value, pop it. Oops, hold on. Okay, that looks good. All right, it's less than or equal to that, then we want to pop it. If not length of A, turn none. Otherwise, head equals node A sub 0. Node equals head, turn head. For X in a sliced at 1 onwards. Node dot next equals node list node node dot next Your answer is 1. That's not right. Last equals 29.7. Last equals a dot pop. Has to be bigger than the last one. Or lesser, strictly lesser than the last one, right? Whoa. Oh, oh no, hold on. Yeah, it should be bigger than the last one, right? What? Okay, that looks right. Kind of hack solution. Let's see what happens. My TLE. Looks like it's going to TLE. Okay. So I have to come up with a more clever way of doing this rather than basically copying it into an auxiliary data structure that is a monotonic stack and then copying it back into a list node. This thing is taking forever. Holy cow. Have to get out and push. Okay, well, while that's running, I'm going to grab some coffee. I have a good feeling this is going to TLE. Okie dokie. Wrong answer. Oh, oh, no mode. Okay, it's not. Oh, I see. Okay, so here. Oops. Well, that sure did take a long time to say wrong answer. The heck. All right. Big money, no whammies. Oh, well, okay, that's not even a right solution. Dang, that sucks. Hmm. 998. Wait, hold on. That's totally wrong. Oops. Okay. That looks right. Okay, well, that's a total hack, and I did not expect that to be accepted. It's pretty lame. 47 minutes, about 11 minutes, plus 2 bugs. Oops. Okay, yeah, so okay, anyhow, this is a total hack going from a linked list to an array, which is a monotonic stack, back to a linked list. Right, so what's another way of doing this? I was thinking recursively, it'd be super cool if we could do that. This, as the recursive stack unwinds, we'd set it to the last biggest one. Keep track of the last biggest one we've seen. Right, so let's try this. All right, here's our hack solution. And let's come up with something better. Right. Solution. Remove nodes. Go node last. So as the recursive stack unwinds, or recursively go in, as the recursive stack unwinds, keep track of the last largest value and point next towards that last largest value as the recursive stack unwinds. And then it has some sentinel value here at the end because the head can get popped off. Sentinel value would be the largest value. Sentinel node, which points to head, has the value of 1e9. Turn sentinel. Next, after we go, node equals head, last equals none. If not, node turn if not last, then this node is the last. I want to go last will be what's returned. Return the largest value you've seen so far, either yourself or in the last. None. Okay, so the last values next should be the largest value. Highest of itself and last. Okay, so go node.next. Last is node. Last is this guy. So last next is going to be this guy, which is what's returned. Next biggest one. So it's either yourself which one's this is last, and that one is the base case. This guy returns none. Hold on, 2, 5, 13. 2, 5, 13, 3, and 8. Okay. So next and last. Okay, so this guy will be last. This guy's the node. That one's no, so there's the base case. Okay, so here's nodes next. Last is this guy. Candidate will be what this guy returns. If not node.next, return node. This guy's 8, so we'll return so either myself or that candidate. Return, okay, so if node.value is less than or equal to candidate value. Okay, so the candidate value is bigger than this guy. We want to take that candidate value. Return a candidate. Otherwise, return the node. So the last dot next is equal to last dot next equals candidate. Rather than yourself, you skip it. Okay, so go. All right, so last will be some sentinel value. Infinity. All right, so it'll be something like this. This guy's last. There's a node. Okay, so node to next here is 8, and that's when we hit the base case, return 8 as the candidate. But this guy, candidate's value is larger than the node value. So last dot next equals the candidate, which will be this guy. I think that looks right. I don't know. Let's see what happens. Uh-oh, node is not defined. Oh, it's list node. Right, list node. Oh, come on. That's not right. Okay, hold on. If it's strictly greater, then we'll bypass it. Okay, that looks right. And then let's see, I missed one. Whatever, we'll just submit it, see what happens. Yay, okay, cool. This is a legit solution. Right, so as the recursive stack unwinds, we update next the last node's next pointer. Okay, cool. Few solutions. As the recursive stack unwinds, update the last node's next pointer. Oh, that looks good. All right, Kotlin, JavaScript. This one was fun. That's cool. It's kind of lame that it was accepted as a monotonic stack there. Like, it'd be cool if it is forced to do the recursive solution. Okay, that's pretty cool. All right, so the last node's value is a candidate value for next. Okay, let's do this again here. Oops, Sentinel equals new list node 1E9 plus 7 is the value. Next pointer, oops, will be head. Turn Sentinel. Next, finds function and return list node pointer. And it takes in a list node pointer, list node pointer. And we'll invoke go on Sentinel and node pointer for last. On go, capture yourself in your own Lambda node. Last, if not node, next, return node. Candidate is go, nodes next node. If the node value is less than the candidate value, then we'll use the candidate value. Node last next is equal to candidate. We can actually do this, I think. Otherwise, we'll return the node. Okay, looks good. It's cool. Okay, bam. JavaScript, we can do the same cool return thing. Head. Okay, let Sentinel equals new list node value will be 1E9 plus 7. And then head will be next. Next, so we'll return, let go. There it goes, sentinel. Last equals null. If not node next, return node. This is the base case. And as the recursive stack unwinds, we'll look at candidate, we'll go node next. Node is last. If node value is less than candidate value, then we'll update last next equals candidate, which will return. Otherwise, it'll return the node. Looks good, right? That's cool. Uh-oh. Oh, no way. I thought I just ran that and it looked good. What the heck? Node, sentinel next. Oh, wait. Yeah, the candidate value exceeds the node's value. Candidates returned. Start next equals candidate, otherwise the node. What am I missing here? Oops. Last next equals candidate, sentinel not next. Oh, I never invoked go. What am I missing now? Okay, there we go. That makes sense. Okay, that's cool. Gotta remember to invoke go. All right, and then Kotlin. Go. Node is a list node. That's our sentinel. Sentinel equals list node. The value will be 1E9 plus 7.2 int. And there is no next. Here's a sentinel. Next equals head. Go. Last equals, oops, so list node, which equals null. If nodes next is equal to null, that's our base case, return node. The candidate is go nodes next, last will be node. And if the node value is less than the candidate's value, then last next equals the candidate, and we'll return the candidate. Otherwise, we'll return the node. Okay, then return sentinel next. Oh, unit was up. This guy needs to return list node. Oops. Okay, no assertion operator is needed, right? Oh. Oops. Okay, yeah, the thing is not null. Okay, looks good. It's cool. And yeah, I'm not gonna do this in Rust. Let's just move on to Q4. Okay, so that's cool. All right, that was fun. And actually, I don't remember that else from this guy. All right, either return that or this guy. That should be good enough. Doesn't need to be perfect, but it's cool. Okay, so there we go. There's that. As the recursive stack unwinds, update the last node's next pointer. If necessary, if needed, or monotonically non-increasing linked list. All right, let's go. Monotonically non-increasing. So it doesn't go up, but it could stay the same or go down. All right, okay, nothing too fancy. Okay, 27 minutes left for Q4. This is where things get a little hairy for me. Q4, we have 27 minutes remaining in the contest. Here we go. Okay. Median equal to K. Ascending order. Integers and nums are distinct. So what are the amount of even and odds? What is the amount of even, odd subarrays with K in the middle? So I found K, expand outwards. It's sorted subarrays. Why is 1, 2, 3? Why is it not 2 though? You think if you sort 1, 2, oh, 3 is not in the middle of 1, 2, 3. Okay. If you sort it, it has to be in the middle. Sort it has to be in the middle. Okie dokie. All right, so the sorted array has to be in the middle of the sorted array. It's okay, it's okay. Go on, go on, go on, go on, go on, go on. Okay, I love you, son. I love you. I want you to go on out of my office so I can. I'm working right now. Okay, I'm doing a LeetCode contest. Go ahead, go on out there. Okay, please and thank you. And you know with Abner and watch the show. Okay, out there in the TV room. Okay, anyhow, back to this. Okay, so got 22 minutes left now. And that's okay. Sorted subarrays, right? The value to the right of it is bigger than it than you count it. The value to the left is bigger than you count it. So we can expand outwards for a quadratic solution. Okay. Let's start off with a TLA solution, then optimize. So the game plan is to find each ith value, ith value, right? It's equal to k, and then this plus one, then attempt to expand outwards, right to the left and then to the right of that pivot. Okay. Right, so that's O of n squared in quadratic solution. My quadratic runtime solution is expected to TLA. Okay. And it's length of A for I in range in if A sub I is equal to K. Then we say JK equals II. While so while they're in bounds and A sub J, let's do this. This would be J, IK, JJ. I is less than that is less than A sub I is less than or equal to A sub J, which is less than or equal to, is equal to A sub K. I'll count it. Count to 0, count equals 1, J minus equals 1, K plus equals 1. Trying to count in the end. 1, that's not right. Thought it'd be at least 2. Come on. This thing should TLE, right? Oh no, it's the wrong solution. Uh-oh. Hope it's 1 expect 3. Oh dang, okay, you can sort those. Okay, it's not quite that naive. 16 minutes. Oops. Okay. Okay. Anyhow, should we consider every separate then as a brute force solution? Or consider all separates, sort and find the median. Right, so my previous brute force solution was not correct. All subarrays ending at each jth index for j in range n or range j I up to j non-inclusive candidate arrays a sub I or 0 to I sorted of length I minus j or j minus I if the candidate n divided by 2, let's see if it's 2 should be 1. Subtract 1 in case if it's even. Minus 1 if not in modulus 2 else 0. Okie dokie, something like that. Nope. N is reference before assignment. What? If not, length of candidate modulus 2. J minus I. Here. What? It is. There's nothing there. What? Up to. Oh, yeah, it should be from I to J, isn't it? I to J? Yeah, I to J. Non inclusive, right? Okay. It's good. That's right. 3, 1, and 3. Okay, so that is a brute force solution. I believe it is correct. And then we can optimize it. It should TLE. Okay, so that TLE is as expected. Got 10 minutes. To go. Right, from brute force TLE to AC. Hopefully. Okay, so that's that. Okay. Right, we have to remember the past to formulate the future. I suppose, right? I mean, it seems like this would be DP. Okay, so how do we optimize this? Right, IndyNet J, and go and check them all. Previous and next. There's 2 values less than it, so it's not even. Like we need balance, right? You need one to be less than it, one to be greater than it in order to expand outwards. How many values are greater than it and how many values are lesser than it as a pivot? 3 lesser, 1 greater. Okay, so ignitives. Next game plan will be to pre-process the input to track values from left to right, which are lesser than, okay. certain equal to k, and from right to left, which are greater than or equal to k. I think we can use that then, right? For each kth value, we don't necessarily need to expand outwards. Greater than k. Greater than k and lesser than k. This is interesting. I think I'm on the right track there. So like for each pivot, I'm calculating. Could do binary search. No, I mean it needs to be near linear. Okay, so either O of n or O of n log n can be accepted since n equals 185, like 100,000. We need a near linear solution for AC. So yeah, pre-process the input. There's 1, 2, 3 values less than 4. It's one value greater than 4. Okay, 5 minutes. I'm pretty sure I'm gonna have to upsolve this one. Get back to it. All the numbers are distinct. I think that's pretty important. One through n. I think this helps, right? This helps. Pretty sure that's key, actually. Deductive reasoning or combinatorics can be used itself. And then how many values are bigger than it to the right? How many values are smaller than it to the left? Yeah, that fourth question, that one always gets me. Yeah. Oh, and they're hard for a reason, right? I need to increase my observational skill set to be a more astute observer. The order doesn't matter. The position matters, right? Because you'll sort them. How many are bigger than it? How many are lesser than it as each pivot? I'm pretty sure, and that sounds legit. So let's do this. 0 times n, r is 0 times n. If a sub I is less than or equal to k. Let's see, L sub 0 equals int a sub 0 is less than or equal to k. And then from 1 to n, we'll build on ourselves. Let's see, L sub I equals L sub I minus 1 plus 1 if that I phi is also less than the k. And then we reset it at k. If a sub I is equal to k, then L sub I is reset because it'd be used for the next k over. All right. 0 or I in range R sub n minus 1 equals a sub n minus 1 is greater than k. Minus 2 down to -1 non-inclusive by -1. R sub I because R sub I plus 1 plus int a sub I exceeds k. If a sub I is equal to k, then R sub I is equal to 0. Left and then print right. Okay. There's 3 less than it. There's 1. So the minimum of those. For I in range n. If a sub I is equal to k, then the number of odds is 1 plus the minimum of that guy, and the number of evens is 1 less than that. That's equals left sub I minus 1 if I minus 1 is in bounds. The minimum of that guy and R sub I plus 1 if I plus 1 is less than n, that's 0. Evens equals odds minus 1. Odds plus evens. Looks good. This might be a clutch move here. Expected answer is 1. Oh, contest is over. 1. Okay, well, I think we're on the right track. We'll come back and upsolve it, right? Okay. To do, upsolve me. Okay, cool. And we'll catch you all next time.